respected all, Dr. Barua sir, Dr. Bruchandi sir, my supervisor Dr. Amol Deshmukh and my colleagues. I am Mrs. Swati Dixit, presenting my pre-submission seminar for Doctor of Philosophy in Electronics Engineering on research topic Design Strategies for Age-Based Image Representation System with VLSI under the supervision of Dr. Amol Deshmukh sir. My place of research is Department of Electronics Engineering, GHRCE College of Engineering, Nagpur. So these are my registration details. My registration was in 2012. These are the papers published. This will be the organization of presentation. So initially I will start with image representation. So image representation is one of the areas used in image processing. It includes segmentation, enhancement and image edge detection. So segmentation is the process of partitioning the original image into meaningful regions or segregation of specific parts of an image. It is very important in medical image analysis and it can be classified into 5 groups: pixel classification, edge-based approach, region-based approach, model-based approach and hybrid approach. So in my research work, I have used edge-based approach. The image edge detection is an important aspect of image processing. It is the process of locating edges of an image, which is very significant step for understanding features of images. So medical imaging is a technique and process used to create images of the human body or for clinical purposes. Generally, colored images are taken into consideration because they show more details such as discontinuities and depth of the field. Color is that attribute of light energy which is related to the wavelength. It helps to carry important piece of information regarding objects of interest in an image, and the same concept is used in color-based segmentation of image. But what we found, there was some problem of segmentation because of the image texture. In reality, the color images are rich in color and texture, and it is difficult to identify the image regions containing color texture patterns. So for grayscale images, segmentation may be easier, but to perform medical image segmentation, the gray levels alone may not be sufficient as many soft tissues have overlapping gray level ranges, and therefore textural properties are useful for image segmentation. Edge detection. Now edges consist of noteworthy features and contain important information. They reduce the size of the image, filters out information that is treated as less relevant, and it preserves the important properties of an image. That's why edge detection is handy in accurately analyzing medical images. It helps in proper treatment of the diseases like tonsillitis, which I have considered for my work. To find out severity of tonsillitis, it is necessary to figure out how much part has been affected. With discontinuities in image of an affected part, the percentage of the disease or presence or absence of disease can be found out. Again, it is a name, edge detection is a name for a set of mathematical methods which aim at identifying the points in a digital image at which the image brightness changes sharply. The points at which image brightness changes sharply are typically organized into a set of curved line segments termed edges. Using MATLAB, it is difficult for real-time implementation, so it can be done by using approaches like fuzzy logic and neural network, but VLSI approach has been found to be very effective and simple, and it is related to FPGA implementation. This is the worldwide scenario. Tonsillitis is initiated by strep throat and it can lead to severe complications if left untreated. According to WHO, every year in around 180 countries, around 1.25 million people suffer from tonsillitis, and due to lack of diagnosis, 0.8 million people reach to the next stage of tonsillitis. So there is no concrete assumption of digital image inspection and analysis, and therefore the analyzed system is supposed to consist of wide set of processing methods and techniques which are based on different properties of the objects of attention. These are some of the terms which are used in my research work. First is Gabor filter, which separates the information based on texture, removing the noise components in image. Chodic algorithm, it is coordinate rotation digital computer algorithm for computing trigonometric, hyperbolic, linear and logarithmic functions. Canny edge detection, this algorithm was developed to give optimal edge detection to provide good edge detection capabilities and good edge point localization. Sorbel edge detection uses two 3x3 special masks which are convolved with the original image to calculate approximation of the gradient, and then log Gabor filter which can work on more than 1 octave bandwidth And so if large data is provided to the system, it provides smoothly with the help of log-Gabor filter. These are the approaches which are used for disease detection system. The first approach was with Gabor filter and quadratic algorithm to detect the percentage of disease. It could show results on computer screen, but the hardware implementation was not possible. Second approach was CAN-edge detection and Xilinx system generator, which are used to detect the severity of the disease, but again the hardware implementation could not be possible using this approach. The third approach was Sorbel-edge detection and Xilinx system generator used to detect severity of the disease. This design supported the hardware implementation and could give better results. And the fourth was using LabVIEW software, where the hardware implementation gave far better results than earlier approaches. This is a generalized block diagram of my disease detection system. Here, the JPG is popularly used format for image, as the images are captured in this format only. The other formats can also be considered for disease detection. So the problem definition is tonsillitis disease detection is the main issue. To detect tonsillitis using VLSI approach and using edge detection technique, so that it will have a biomedical approach. To design a simplified disease detection system with new techniques, for example with Xilinx system generator and LabVIEW environment, which will be somewhat simpler, not complex. Then the design strategies used for disease detection system, the particular parameters are considered like different filters and different edge detectors. The hardware implementation is done twice using Sorbel-edge detection, one with system generator and another with LabVIEW environment. The resources are optimized using hardware and compared with other works that have been already done. For Xilinx system generator, the clock frequency is set at 50 MHz, and the strategies can be used for other biomedical applications where the edge detection is required, like for fracture detection also, or for finding out any faults in the bottleneck of a bottle. Again, this system can be used. So, I am presenting now the literature review for this research work. So, in this paper, they have proposed a new method for segmenting the fibroid in uterus using concepts in mathematical morphology. It completely avoids over-segmentation, which is a major problem. In this paper, the authors have proposed traditional fuzzy Hopfield neural network as one of the excellent segmentation methods. It segments the image more clearly, continuously, smoothly, and has better capability in noise immunity. The proposed approach possesses an important significance on computer-aided diagnosis based on medical image segmentation. In third paper, they have proposed that medical image segmentation requires filters that consider the textural properties of the image, and gray level alone may not provide the complete information of the color images, and that's why Gabor filter is used. In this paper, they have proposed novel idea for implementing Gabor filter, which is high speed. This paper, they have given tonsillitis detection model using size feature and color feature, and from analysis they have given the threshold limit for detection less than 30. In this paper, the authors have described the real-time implementation of Sorbel operator color image edge detection using FPGA, and in order to achieve real-time implementation, parallel architecture is designed. This paper, the authors have explained implementation of several edge detection algorithms like Sorbel, Privet, Robert and Compass, and then they have made comparative study. This paper, new area optimized VLSI architecture for color edge detection using Sorbel operator is designed and implemented on Vertex 5 FPGA. This paper presents a design of CAN-edge detection algorithm to find H pixels in grayscale image, and Xilinx ISC Design Suite 14 software platforms are used to design algorithm using VHDL language. Here, the authors have presented a design of Sorbel edge detection algorithm to find H pixels in grayscale images. In this paper, the authors have presented a real-time hardware image processing system which is based on FPGAs and chosen image processing algorithms implemented for edge detection. Again, in this paper, they have used detection of diseases like tonsillitis, tumor fracture, and they have done this using log-Gabor filter. So, based on all these papers, I have tried to minimize the usage of resources. Then, without actual VHDL coding, I have tried to design some block sets which will be helpful in generation of the VHDL code without actually coding. So image segmentation, this approach was used for disease detection of the tonsillitis using edge detection. The design of tonsillitis detection system is done using MATLAB and Model Sim. This is used to locate the objects and boundaries. The process of assigning a label to every pixel in an image such that the pixels with the same label will share certain visual characteristics. This approach provides an idea for efficient Gabor filter design with efficient noise reduction and reduced memory storage. It is suitable for detecting the early stages of the disease using textural properties of the image. This is a block diagram for disease detection using Gabor filter, and this block diagram consists of basically 6 modules. The first is MATLAB image reading module, second is Gabor algorithm, third is image segmentation module, then disease detection or decision making module, VHDL output module, and final result display module in MATLAB. So the image reading and resizing module reads 2 RGB images from the database for comparison. One is healthy image and another is having disease features. The images can be of different sizes and are resized in fixed format, and images are further processed by segmentation unit which are coded in VHDL. It takes only binary form of data for processing, but other forms are not supported. It is necessary to convert the pixel data of images in binary form. The image file format uses 8-bit pixels, and the code for converting image data into binary form is written in MATLAB, and result is stored in do file in predefined location. So this slide is showing the do file wherein the image pixel values are converted into binary form. So these files will be applied, will be used in Model Sim software. Then Gabor filter. Since the Gabor filter is useful for textural properties of the image, so the RGB color space defines a color as percentage of red, green and blue hues which are mixed together. 3 Gabor marks for RGB are required for filtering such images. Then need of coding algorithm, because the Gabor filter consists of some trigonometric terms, therefore this algorithm is used, which is a shift and add algorithm, uses only right shifts and additions, minimizing the computation time. Then image segmentation module. Here it is to apply the Gabor filter to the image for filtering the noise component. These are disease detection and decision making module data flow. Step 1, where is input images are captured from CCD camera. Second is pre-processing, step to step input pixels. Third is in feature extraction, RGB space is found and green space is used to decide the tonsil area. The 2 images are stored in 2 buffers and are compared, and overlapping region between the infected area and healthy area is calculated by this model. And this difference is compared with the threshold level and a decision is taken based on that. Then VHDL output module. The output from step 3 would be stored in text file and an output file would be generated. This would contain the actual output image results like this. Now here, if the images are matched, if the file contains the comparison, if values are pixel of match, then we get 255 or otherwise 0, and from this text file the percentage of the disease can be found out. A simple MATLAB code named as postfile.m, which would take the difference output from the text file, then calculated the percentage and displayed it on MATLAB screen. If the percentage of difference is less than 30, then disease is not detected, or otherwise the disease is detected, this message is displayed over here. But like that, this is the final result display model. But there, the hardware implementation was not possible with this system. This is the paper published on this work in International Journal of VLSI Design and Communication, VLSI CS. Sir, myself.
You should write the authors.
Yes, sir. These all are my publications that I have not given.
Oh, your publication. Yes. Why not? I mean, is it single author?
No, not along with my
Right.
supervisor also. Yes, sir. This is the second architecture using canny edge detection. It is showing the block diagram. It uses Xilinx system generator as a developing environment, uses the system generator block sets to design the architecture, and complete architecture design in MATLAB Simulink and implemented in ISC design suite. First, the images is filtered to remove the noise present. Then Gaussian filtering is used. The edge detection of image is implemented by VHDL block sets. Here VHDL programming is not required actually. And code is generated through Xilinx system generator and synthesized in ISC design suite. This algorithm runs in 4 separate steps. Smoothing, which is blurring of the image to remove the noise. Then finding gradients. The edges should be marked where the gradients of the image has large magnitudes. Non-maximum suppression is to trace the edge in edge direction and suppress any pixel value that is not considered to be an edge. And then edge tracking by hysteresis. That is, hysteresis is used for removing the stacking from an image. System generator enables the use of simulink for designing Xilinx FPGAs. Available versions are 13.1 and MATLAB 12 wherein this design is done. It has been configured with MATLAB 12 and after configuration it produces Xilinx block-stretch library in Simulink which is used for VHDL design. So this is the diagram which is showing the conversion of the image through gateway in and gateway out for system generator, because there the image is needed to be converted to 1D. So it is given to gateway in, then processing is done in between gateway in and gateway out, and then again the image is converted to its normal form, that is 2D image. This is the block set for designing the Gaussian filtering, which uses 5-line buffer sequential stream of fixes to construct 5 lines of output. This is the diagram which is designed in the Xilinx system generator, image non-maximum suppression, and these are the results of Gaussian filtering and non-maximum suppression. This is the basic image which is considered. Then design of Kenny edge detection system in Xilinx system generator wherein different blocks are used. And the implemented design is synthesized in ISC Design Suite 13.1 and it produced device utilization summary for hardware implementation like this, wherein we can find out the utilization of the resources.
ऐसा ब्लूटूथ है धक्का लगता है विषय मैडम अच्छा हो रहा है अच्छा चल जा रहा है अरे चाह देना दे अंदर नहीं चल ना
आमचं
this is the device utilization summary in Xilinx ISC Design Suite 13.1, wherein the utilization of the resources is given, and this utilization can be compared with the work that is already done. This is for vertex 5, but this was in system generator only. Again, hardware implementation could not be possible with this system, but it is giving the device usage over there, and this is for another vertex 5 pin. These are the output results for canny edge detection algorithm with noise reduction, then non-maximum suppression, and then edge detection. So the tonsils image, which is considered for my research work, again the edge detection of those images were also done. It is for normal tonsils edge detection. This is for affected tonsils edge detection. And in this work, with the comparison of these two edge detections, we could find out whether the disease is present or not. Again, since it was not possible with hardware, we had tried to do some comparison on standard parameters like mean, standard deviation and variation values, and from these values also we can say whether the disease is present or the percentage of disease is more or lesser side. So again, sir, sorry, I have not put names of authors over here. These are the papers published by me only, along with my supervisor. Then this was the yes.
What are the journal name? International Journal
of Current Engineering and Technology. This is the third architecture using Sobel edge detection. Again, the same block diagram is there, only filtering is different and Sobel edge detector is used. Using Xilinx system generator as a developing environment, it uses the system generator block sets to design the architecture. The complete architecture design is done in MATLAB Simulink and implemented in ISC Design Suite. An image is needed to be filtered to remove the noise present in it. For filtering the original image, filtering masks is used. And next step is generation of the VHDL code through Xilinx system generator. The Sobel filter uses two 3x3 special masks as given, convolve with the original image to calculate the approximations of the gradient. Then VHDL synthesis is a process where a VHDL is compiled and mapped into an implementation technology such as FPGA or ASIC. The implemented design is needed to be synthesized in ISC Design Suite 10.1. It produces the device utilization summary for hardware implementation, and the VHDL code needed for the synthesis is generated by system generator, and code generation process takes several minutes and can be generated for various families of the code, wherein the 50 MHz frequency is used over there. The implementation on FPGA, the edge detection in grey images does not give very accurate results due to loss of color information during color to grayscale image conversion. So, the FPGA implementation provides the possibility to perform the algorithm modifications in later stages of the system development. So, this is a complete Sobel edge detection algorithm using system generator, wherein the RGB grey adds up gateway in, gateway out, video viewer, absolute, DAFIR for filtering, subsystem and system generated token and resource estimators are used for design of this system. So, after the design in system generator, the system is to be prepared for hardware software co-simulation, wherein this hardware software co-simulation tag is developed like this, as shown in this diagram, and this block is used in the system generated design, wherein we will get the output results. So this was the setup which was used for hardware implementation, and here the software and hardware results are compared, wherein the hardware results were better than that of software. So this was the basic image considered, and these are for the tonsillitis detection. This was for normal tonsils, this was for affected tonsils. This was the comparison test for both the images. Here also the comparison test, and here again the mean, standard deviation and variance are calculated for normal images and affected images. Then after hardware implementation, this was the device utilization summary for Spartan 3XE 3S200, which give the utilization, that is number of slices 23%, number of slice flip-flops 20%, and the same device utilization summary was compared with the works earlier done with Spartan 3 and 3A kits, wherein we could find that this here utilization was lesser than these works. Then these are the papers published on this work. Then the next strategy is LabVIEW and log-Gabor filter for disease detection. The stages preferred for this are the selection of edge detection operator. Sobel edge detection operator is selected for tonsillitis detection on the basis of its performance. Then LabVIEW is selected on the basis of application simulation software, since real-time implementation on FPGA is possible through LabVIEW environment. In medical application, only software is not considered fully trustworthy, but for real-time implementation, hardware is required. So FPGAs are used for real-time implementation as they give high performance ability and also used for real-time application. So this is the architecture flowchart for LabVIEW environment wherein disease detection is done. Sobel edge operator gives best contrast ridges and sharp edge, so accurate tonsillitis detection is possible. By using log-Gabor filter, work can be done on more than 1 octave bandwidth. So even if number of images are provided to the system, it works smoothly. LabVIEW is the environment for digital image processing. If VHDL code is written for this algorithm in FPGA, then it is too time consuming and bulky. But with the help of LabVIEW, it becomes easier to generate the VHDL bit file for hardware implementation. So image processing on LabVIEW, it is a graphical programming language and totally supports the image processing, and FPGA implementation is possible in LabVIEW. Disease detection module is designed in VI editor, which is virtual instruments are designed over there, which is a graphical code designer of LabVIEW, and with the help of NI platform, which is used for image processing. After completion of the design with LabVIEW and its design tool, it is implemented on FPGA platform for real-time processing. Then this is the input image selection process, which is where image is required for processing. It is selected either from the camera or from computer database. After the operation on LabVIEW, disease detection results are displayed on front panel of the LabVIEW screen. The disease detection design implemented on SBRIO 9631 FPGA board for fast image processing and for real-time application in medical field. And FPGAs are frequently used as implementation platforms for immediate image processing applications. Then VHDL code generation by LabVIEW FPGA is done. Once the LabVIEW FPGA code design is completed, hardware implementation file gets created using FPGA code compilation. So this is the FPGA SBRIO 9631 board wherein the LabVIEW code is done. This is the design and implementation process. The methodology for disease detection depends on edge detection. With the help of different tools and platforms provided by National Instruments, LabVIEW can work on image processing. So input image is given through image acquisition box. These all are virtual instruments. Then the pre-processing of LabVIEW in which one particular color is extracted from the image so that resultant gets digital image in the form of grayscale image. So this is the diagram which is showing virtual instruments which are showing the color plane extraction of the image, and these are the results of that color plane extraction. Then this is a LabVIEW program for using Sobel operator in LabVIEW environment, and for log-Gabor filter design, this math toolkit of MATLAB is called in LabVIEW environment because it was not directly, we could not design it directly in LabVIEW. It was implemented on SBRIO for high performance and to reduce the time consumption. Sobel operator is well suited for tonsillitis detection as it gives better results as compared to others. Hardware and software results were compared after the implementation of the disease detection module, and it was found that the operation time got reduced after simulation with the hardware. Though the simplicity of LabVIEW made it easy to design any image processing operation with the help of its supporting platforms and tools. I have tried over here the comparison of all strategies used, the 4 strategies which I have used, wherein the hardware part was possible with those 2 strategies, Sobel edge detection with system generator and log-Gabor filter in LabVIEW. Then edge detection was possible in all the strategies. Then software part, again it was possible with all the strategies, and real-time implementation could be possible with again last 2 strategies. And speciality of first system was it helps in early stage detection of the disease. It exactly gives the percentage of the disease present. Second strategy was it could give device utilization summary. In third strategy, it could give device utilization summary to compare with earlier work, and time required could not be calculated over there. And in fourth strategy, the time required could be calculated, and this is detected on the basis of histogram values. These are the paper publications on this overall work. Some of the papers I have mentioned earlier. These are all are the overall papers which are published on research work. Then there is these are the references for this research work, and available database is with me, which is taken from the medical sciences science college, and doctors have given this site sciencefotolibrary.com for testing of the images, because they do not provide direct images, and those images are not taken with direct camera. Those are different images with tomography. These images for this work we can collect by camera only. It can be done.
How do you digitize them?
Yes, sir.
How do you digitize? Because
Yes,
you
sir.
need the data in matrix form.
Yes, sir.
How do you get that?
Yes.
You will get that.
What, sir?
Will you get the data in a grayscale or in color images?
That is to be converted then.
That is to be converted.
Colored
These
images.
is to be converted.
Yes, sir. That is to be converted.
So I have some observation, because I have little objection about the word VLSI. I cannot find much of your work on VLSI. Number one. Number two, you see, for last 20 slides you were rather praising the lab view for NI software. It is very difficult, I mean, if the thesis go outside your country, I mean, India, and they will try to find what is the new thing you have done. You have several papers, I do agree. One is ITV also. That is appreciable. The thing is that, I mean, if you just compare your work with in the lab view environment, that will not lead you to thesis, your PhD degree. So that is something you have to do, not to praise only lab view or the NI software.
But
And the VLSI also, I cannot find much of the VLSI here. So either you change the title of your thesis. Okay. You have done substantial work, that you have studied so many things, you have learned so many things more, applications of the library, that is also good. So the thing is, in the PhD work, you have to done something new, which you have already done, because that is the reason which you need to paper. But here, this word VLSI is not really appreciated.
FPJ implementation.
Examiner will object if it goes outside. That is my observation. When you directly write the Good work.